Hi, for today's video, I'd like to look at z-scores when dealing with normal distribution functions. Now, to set up the reason why z-scores are relevant or useful, I wanted to look at some guy named Sergio who took a bunch of tests for midterms, and here you can see his scores, and here you can see the average for the rest of the class and the standard deviation. Now, if we were asked to rank his scores from best to worst, or worst to best, you might suggest that the biology score is the worst score that he did. However, you'll recognize after further examination that in biology, he scored 10 points above the mean. So even though he got a 72, average kids got 62%. And the spread of the scores, turns out most of, or about 2/3 of the scores, are going to be within 12 points above or below 62%. So almost all of the scores were ranging somewhere between a 50 and a 74. So a 72 is on the top end of that, which is pretty decent. Take on the other hand is German score, which is the highest score on the list, but the average for the class was 96 and the spread was 9.6. And therefore, the 91% is only about a half of a standard deviation above the mean. So even though his gross score was high in German relative to the difficulty of the test, he didn't do that well compared to his peers. So in this case, because all of the means and standard deviations are different, we have to do a little bit of mental gymnastics to determine which of these scores is the best. In comes z-scores. Now, before we do this a little bit, or before I talk about z-scores specifically, I wanted to look at a hypothetical. If I told you you scored 56 points on an IB physics test, and then asked you how well did you do, the correct answer would be, it depends. There's no way you know that 56 is a good or a bad score unless you know a couple things. Obviously, you'd like to know what the highest score is possible, but forgetting that right now, we would just actually look at what else would you need to know to determine relatively how well did he do. 56 is only as good as the mean in the standard deviation. So 56 is a good score if the average was 20. It's an okay score if the average was 55, because he's just slightly above average. And it's a kind of a bad score if the average was 75. So it's important to know where your score stands relative to the rest of the class. So that's what the mean does. What about the standard deviation? Well, let's suppose that the average was 50, and I got a 56. Well, if the standard deviation was 3, then a 56 is really good. But if the standard deviation is 12, then a 56 is only halfway to being one standard deviation above the mean. So, looking back at Sergio's tests, we can observe that by comparing the performance relative to the test of the class is difficult because the standard deviations are all different. It would be ideal if the distributions of their scores were all transformed so that they could be compared to the same bell curve. And that's where we enter z-scores. To understand this a little bit more, I want to look at the score of 56 in a little bit more detail. Suppose the mean was 50 and the standard deviation was 3. Then a score of 56 is 2 standard deviations above the mean. So here you can see the bell curve with the mean at 50, and the score of 56 is from 53, 56. It's 2 standard deviations above the mean. So, way to calculate how far above the mean you are, first you can say 56 points is 6 points above the mean, and the standard deviation is 3, which means if we take 6 points divided by 3, we know that we are 2 standard deviations above the mean. To be 2 standard deviations above the mean, as you can see from looking at the bell curve, is an extremely rare event. So getting a 56, if the mean was 50 and the standard deviation was 53, or was 3, then that's a really good score. That same 56, with the same average of 50, but a standard deviation of 12, is suddenly not quite as desirable, because with the standard deviation of 12, dude is halfway to being 1 standard deviation above the mean. So, if you were to do the same calculations here, you could take 56 is 6 points above the mean, but instead of dividing by 3, you divide by the standard deviation of 12, and you get 6 divided by 12 is 1/2. So the z-score for 56, if the standard deviation is 12, is 1/2. The z-score for 56, if the standard deviation is 3, is going to be 2. So, summarize, what does a z-score tell us? It tells us that we can basically say the mean is always going to be at 0, and the standard deviation is always going to be at 1, and a z-score is going to tell us how many standard deviations above or below the mean we are. So if the z-score is 2, we're 2 standard deviations above the mean. If the z-score is -1, we're 1 standard deviation below the mean. All you have to do is recognize the calculation. It's we could take the score that we got, subtract the average, and divide it by sigma. You might recognize x minus mu over sigma. That shows up in the equation for the normal distribution. So if I got a 47 with a mean of 50 and a standard deviation of 3, then we can say a 47 is 3 points below the mean, and the standard D is 3, so we are 1 standard deviation below the mean. What if I got a score of 50? 50 is 0 above the mean, standard deviation is 3, so a score of 50 is 0, which means you struck the mean exactly right. So once you have all your scores converted into z-scores, then you can figure out the best z-score is the one score that is the highest number of standard deviations above the mean. So if we were in class, you'd be able to take all of these and subtract the mean, divide by the sigma, and you will have your z-score. And then the highest z-score is the furthest above the mean. So that's what that's all about. So essentially what we're doing is we're taking a normal distribution, much like this one, a normal distribution whose mean is 50 and whose standard deviation is 3, and by doing this transformation, the specific z transformation, subtracting the mu and dividing by sigma, you're officially shifting or transforming your normal curve so that it matches the exact basic normal curve. So the standard normal curve has a mean of 0 and a standard deviation of 1 no matter what. So again, if you really want to summarize what is a z-score, it's just a number that will count how far above or below the mean your score happens to fall. Now, when it comes to the graphics display calculators, they're quite elegant because they are automatically programmed in with the standard normal distribution. So if you use the normal CDF function, and let's say you wanted to find the probability that a certain score exists, so you want to find the probability of this particular outcome. If you are using the z-curve, all you have to do is type in normal CDF. You go from -infinity up to the point A, and the normal CDF is going to give you the shaded area under the curve. Now, if you'll notice, what's missing here is I did not have to say the standard deviation, and I did not have to say the mean. Because if you use normal CDF and you do not state the mean and the standard deviation, the default is going to be a mean of 0 and a standard deviation of 1. So basically, your calculator is programmed in with the standard normal, and if you do not specify a mean or a standard D, you are going to get just the bell curve. So I hope you find that helpful. Always email me with questions, and have a good day.